May 19, 1941. 30,000 feet above the Mojave Desert, Major Signer Gilkey pushes the control yoke of his P-38 Lightning forward. The twin Allison engines roar as the silver fighter tips into a dive. Gilkey is testing America's fastest fighter, a radical twin-boom design that looks like nothing else in the sky. He's supposed to check handling characteristics at high speed. Standard test protocol. Routine. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. At 25,000 feet, the airspeed indicator climbs past 320 miles per hour. Then something goes wrong. The tail begins to shake. Not a gentle vibration, a violent, bone-rattling hammering that threatens to tear the aircraft apart. Gilkey pulls back on the yoke. Nothing happens. The nose tucks under, steepening the dive. He pulls harder. The controls feel like they've been welded in place. Physics has stopped listening to him. The Lightning accelerates toward the desert floor like a thrown spear. 30,000 feet becomes 25,000. 25 becomes 20. Gilkey knows the numbers. At this dive angle, he has maybe 90 seconds before impact. He tries everything. Full back pressure on the yoke, elevator trim wheel cranked to maximum nose up. The aircraft ignores him. The controls are locked solid, frozen by invisible forces that 1941 aerodynamics couldn't explain. 18,000 feet, 15,000. The ground resolves from brown haze into individual features. Mesas, dry lake beds, places that will become his grave. Then something shifts. At 12,000 feet, the shaking lessens. At 10,000, he feels the slightest give in the elevator. He works the trim tab, inch by excruciating inch. The nose comes up, barely, just enough. Major Gilkey pulls out at 8,000 feet with his heart, trying to punch through his ribs and sweat freezing on his face in the unpressurized cockpit. When he lands at Muroc Army Airfield and climbs out of the cockpit, his hands are still shaking. The ground crew asks if he's okay. He tells them he just rode a fighter airplane that tried to kill him, and he doesn't know why. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Major Gilkey files his report that evening. Control lockup in high-speed dive. Aircraft became unrecoverable above 12,000 feet. Cause unknown. The report lands on the desk of engineers at Lockheed's Burbank facility, who have been hearing whispers about this problem for months. Test pilots describe it in hushed tones. The Lightning stops flying and starts falling. And once it starts falling, nothing can stop it. The engineers call it compressibility, but nobody really understands what that means in 1941. The word exists in aeronautical textbooks as a theoretical concern, something that might happen if an aircraft approached the speed of sound. But the P-38 isn't approaching the speed of sound. It's diving at 350, maybe 400 miles per hour, well below supersonic velocities. Yet somehow, the air itself is changing properties, turning from a fluid that lifts wings into something more like concrete. The laws of flight are breaking down, and pilots are dying because of it. This wasn't just an engineering problem. It was a death sentence for America's most advanced fighter program. The Lockheed P-38 Lightning was supposed to dominate the skies over Europe and the Pacific. Twin engines for redundancy, heavy armament, speed and altitude performance that would make it untouchable. Instead, it was bleeding pilots who got into dives they couldn't escape. And the worst part? Nobody knew how to fix it. What the engineers at Lockheed didn't realize yet was that solving this problem would require understanding physics that hadn't been fully explored, testing facilities that didn't want to cooperate, and solutions that would cost lives before they worked. The answer wouldn't come from textbooks or wind tunnels. It would come from desperate experimentation, from engineers willing to try ideas that looked absurd on paper, and from test pilots brave enough to fly prototypes that had already killed their colleagues. The P-38's compressibility problem was about to force American aviation into territory where theory ended and survival began. And at the center of it all was a young engineer named Kelly Johnson, who understood something the Army Air Corps refused to believe. The Lightning wasn't broken, Physics itself was the problem. And fixing physics required changing the airplane in ways that seemed impossible. The story of how one team solved an unsolvable problem begins not with success, but with failure and death. Because before the dive flaps saved hundreds of pilots, Lockheed had to learn what wouldn't work. And that lesson came at the highest possible price. The Lockheed P-38 Lightning didn't look like other fighters because it wasn't designed like other fighters. When Army Air Corps Lieutenant Benjamin Kelsey and Lieutenant Gordon Saville drafted the specification in February 1937, they wanted something revolutionary. An interceptor that could reach 400 miles per hour, climb to 20,000 feet in 6 minutes, and carry enough armament to destroy bombers in a single pass. They called it Circular Proposal X-608. Most aircraft manufacturers looked at those requirements and politely declined. The numbers seemed impossible. Lockheed's chief engineer, Hall Hibbard, and his brilliant young protégé, Clarence Kelly Johnson, looked at the same requirements and saw opportunity. Johnson was 27 years old in 1937. Fresh from the University of Michigan with a master's degree in aeronautical engineering, he'd already made a name for himself by telling his boss that Lockheed's new Model 10 Electra had a tail design that would kill people. He was right. The tail was redesigned. From that moment, Hall Hibbard knew Johnson possessed something rare, the ability to see problems others missed. The twin-boom configuration Johnson sketched wasn't aesthetically driven. It was brutally practical. Put the engines in pods on the wings, run turbocharger exhaust through the booms, mount the guns in the nose where they wouldn't have to fire through propeller arcs, create a weapons platform that was actually a flying gun battery with enough power to reach altitudes where German bombers operated. The Army Air Corps liked what they saw. On June 23, 1937, they authorized Lockheed to build a prototype. Cost $163,000. The XP-38 prototype first flew on January 27, 1939, with Lieutenant Kelsey at the controls. It was spectacular. Sleek, fast, and powerful beyond anything the Air Corps had seen. 2 weeks later, Kelsey attempted a transcontinental speed record, flying from California to New York in 7 hours and 2 minutes. Just short of breaking Howard Hughes's record, but impressive enough to generate newspaper headlines across the country. Then, disaster struck. Approaching Mitchell Field on Long Island, both engines died. Kelsey glided the XP-38 into a golf course. The prototype, irreplaceable and hand-built, was destroyed. But the Air Corps had seen enough. They ordered 13 YP-38 seconds for service testing. These weren't quite production aircraft. They were refined prototypes, each one assembled carefully to prove the design worked before committing to mass production. The first YP-38 finally rolled off the line in September 1940. By early 1941, test pilots were ringing them out, pushing them through their performance envelope. That's when the problems started showing up. High-altitude dives produced a phenomenon nobody expected. Above 20,000 feet, when pilots pushed into steep dives, the aircraft would begin shaking violently. The tail buffeted so hard it seemed like it would tear off. Worse, the nose would tuck under, steepening the dive. And then the controls would lock, completely. Pilots couldn't pull out. They could only ride it down and hope that when the aircraft reached denser air at lower altitude, the controls would unlock before they hit the ground. Major Signer Gilkey's experience in May 1941 crystallized the terror. He'd been seconds from death, saved only because he had enough altitude to wait for the aircraft to slow down naturally as it descended into thicker air. Other pilots wouldn't be so lucky. The Army Air Corps initially suspected tail flutter, a known aerodynamic problem where flexible control surfaces oscillate at certain speeds. Flutter had killed test pilots before. The solution was usually strengthening the tail structure. Lockheed's engineers went to work. They installed fillets where the cockpit gondola joined the wing center section, smoothing the airflow. That solved some of the buffeting. But the nose tuck and control lockup persisted. Kelly Johnson knew they were dealing with something else, something that didn't fit the flutter profile. In a 1937 engineering report, Johnson had actually predicted this possibility. He'd written about concerns regarding high-speed flight and compressibility effects, but in 1937, nobody really understood what that meant in practical terms. The word compressibility described what happens when air molecules can't get out of the way fast enough. At low speeds, air acts like an incompressible fluid, flowing smoothly around wings and control surfaces. But as speed increases, especially when parts of the airflow locally accelerate over curved wing surfaces, something changes. Air molecules start piling up. They can't move aside fast enough. Shock waves form, pressure distributions shift dramatically, and the behavior of wings, control surfaces, and entire aircraft becomes unpredictable, dangerous, fatal. The P-38, with its clean lines and powerful engines, could dive faster than any American fighter in 1941. In a power-on dive from high altitude, the Lightning could approach 450 miles per hour. That's nowhere near the 760 miles per hour speed of sound at sea level. But at 30,000 feet, where the air is thinner and colder, sound travels slower, about 660 miles per hour. More importantly, the airflow over the top of the P-38's wing accelerated locally to even higher velocities than the aircraft's overall speed. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now, back to the story. This meant that, even though the P-38 was flying at 400 miles per hour, the air rushing over the wing's upper surface could be moving at 500 or even 550 miles per hour. At those speeds, localized shock waves formed. The smooth airflow separated from the wing surface, lift collapsed, and the center of pressure, the point where all aerodynamic forces effectively acted, shifted dramatically rearward. That rearward shift of the center of pressure created a massive nose-down pitching moment. The aircraft wanted to dive more steeply. And here's the killer. Those same shock waves disrupted airflow over the tail surfaces and elevators. The pilot's controls, which worked by deflecting airflow over the elevator, suddenly had no airflow to deflect. The elevators might as well have been welded in place. Kelly Johnson understood the theory. What he didn't understand was how to fix it. In 1941, aerodynamic theory hadn't caught up to aircraft performance. The P-38 was flying faster than any fighter before it, entering a regime where pre-war wind tunnel testing hadn't ventured. NACA, the National Advisory Committee for Aeronautics, operated high-speed wind tunnels that could simulate these conditions. But there was a problem. Wind tunnel operators were terrified of damaging their expensive facilities by running tests at transonic speeds, where shock waves could wreak havoc on sensitive instrumentation. Johnson requested access to NACA's wind tunnels at Ames Laboratory in California. The initial response was lukewarm. Wind tunnel time was precious. Other projects had priority. The war in Europe was escalating, and everyone needed testing. Months passed. The Army Air Corps kept pressuring Lockheed to solve the problem. Production contracts were on hold. The Lightning was supposed to be operational by late 1941. Instead, it was grounded for testing, while engineers chased a phenomenon they couldn't fully explain. By autumn 1941, Lockheed had a few ideas for solutions. None of them had been tested. All of them were theoretical, and testing them meant putting pilots into aircraft that had already demonstrated lethal tendencies. The first proposed solution involved servo tabs, small auxiliary control surfaces mounted on the trailing edge of the elevators. The idea was elegant. When a pilot pulled back on the control yoke, the servo tabs would deflect, creating aerodynamic forces that helped move the main elevator. If compressibility was making the elevators too heavy for pilots to move, maybe servo tabs could multiply their effort. Lockheed designed spring-loaded servo tabs that would activate when control forces exceeded 30 pounds. Below that threshold, they'd remain neutral. Above it, they'd deploy and assist the pilot. On paper, brilliant. In practice, nobody knew if it would work at 400 miles per hour in a compressibility lockup. That's where Ralph Virden came in. Virden was 43 years old in November 1941. An experienced test pilot with thousands of hours, he understood the risks. Lockheed briefed him carefully on the servo tab installation. Fly the test sequence at high altitude. Document handling characteristics. And critically, do not push the aircraft to high speeds at low altitude. The servo tabs were designed to help at high altitude, where control forces were heavy. At low altitude in denser air, they could exert so much leverage that they'd overpower the structure. A note was taped to the instrument panel reminding Virden of this restriction. November 4, 1941. Virden climbed into YP-38 No. 1, the same aircraft Major Gilkey had barely survived in May. The servo tabs were installed. The test sequence was planned. Virden took off from Burbank, climbed to altitude, and began his tests. Everything went smoothly. The servo tabs seemed to help. Control forces were lighter. After 45 minutes, Virden radioed that he was coming back. Successful test. No problems. Then, 15 minutes later, observers on the ground saw YP-38 No. 1 in a steep dive, not a controlled descent, a near-vertical plunge with the engines screaming. At 3,000 feet, the tail assembly separated from the aircraft. The Lightning cartwheeled through the sky, shedding pieces, and smashed into the ground near Bakersfield. Ralph Virden died instantly. The Lockheed engineering team was devastated. They'd sent a man into the sky in an aircraft they'd modified, and he'd died. The investigation revealed what happened. Virden had completed his high-altitude tests successfully, but on his way back, either through curiosity or inadvertence, he'd put the aircraft into a high-speed dive at lower altitude. The servo tabs, working in denser air where their effectiveness multiplied, had exerted such tremendous force on the elevator that the entire tail structure failed. The tabs had literally torn the tail off the airplane. Kelly Johnson wrote in his notes that night that the servo tab solution was dead. They'd tried to solve compressibility with a mechanical assist, and they'd killed a test pilot. The Army Air Corps concluded what Johnson already knew. Servo tabs weren't the answer. But if servo tabs wouldn't work, what would? The Lightning was in production. Orders were piling up from the Army and from Britain. Pilots needed fighters. And Lockheed had an aircraft that was magnificent in every way except for this one fatal flaw. It couldn't dive without killing its pilot. The pressure on Kelly Johnson and his team became crushing. December 7th, 1941, Japan attacked Pearl Harbor. America was at war. The P-38 was desperately needed. But sending pilots into combat in aircraft with known control lockup problems wasn't just irresponsible, it was murder. Production continued, but with restrictions. P-38 pilots received explicit instructions. Do not exceed certain speeds in dives. If you enter a compressibility lockup, reduce power, extend gear if possible to increase drag, and wait for the aircraft to slow down naturally. Pray you have enough altitude. These weren't solutions. They were survival strategies. Kelly Johnson knew that fixing the P-38's compressibility problem would require understanding something fundamental about high-speed aerodynamics that nobody had fully grasped yet. The clock was ticking. Pilots were training on Lightnings. Combat deployment was months away, and somewhere over the skies of Europe or the Pacific, American pilots in P-38 seconds were going to get into dives they couldn't escape, unless Lockheed found an answer. Fast. By early 1942, Lockheed's engineering team was desperate. They'd eliminated tail flutter, they'd tested servo tabs and lost Ralph Virden. They'd tried external mass balances, thickened tail skins, modified elevator geometries. Nothing worked. The P-38 still entered. Compressibility lockups that killed pilots. And worse, combat units in the Pacific and North Africa were beginning to receive Lightnings, with explicit warnings in the pilot's manual. Do not exceed certain dive speeds. If you enter compressibility, reduce power and pray. German and Japanese pilots learned about the P-38's weakness quickly. Luftwaffe intelligence briefings in late 1942 specifically mentioned it. If a P-38 bounces you at high altitude, don't try to turn with it. Don't try to climb away. Just roll inverted and dive. Dive steeply. The Lightning can't follow you down. Its controls lock up. You're safe. This tactical reality was killing American pilots before they even encountered the enemy. The knowledge that their aircraft had a fatal flaw eroded confidence. Some pilots requested transfers to P-40 or P-47 squadrons rather than fly Lightnings. Kelly Johnson knew the answer wasn't going to come from incremental fixes. They needed to understand the fundamental physics of what was happening. That required wind tunnel testing at speeds nobody had dared attempt. In his autobiography, Johnson later wrote that he pleaded with NACA, the National Advisory Committee for Aeronautics, to test a P-38 model in their high-speed wind tunnel at Ames Laboratory in California. The response was lukewarm. NACA engineers had previous experience with models thrashing violently at near-sonic speeds. They were terrified of damaging their expensive wind tunnel. The machinery was delicate. Shock waves could wreak havoc on instrumentation. And honestly, they didn't want to be responsible for equipment failures during wartime when every facility was critical. Johnson kept pushing. Months passed. P-38 seconds were rolling off production lines and going into combat with a known killer defect. Finally, someone with enough authority intervened. General Henry Hap Arnold, Chief of the Army Air Forces, heard about the impasse. Arnold was a pilot himself. He understood what compressibility meant to men in combat. He issued a direct order to NACA. Test the P-38 model. Test it at whatever speeds necessary to understand the problem. That's an order. Do it. In late 1942, NACA engineers at Ames Laboratory reluctantly wheeled a scale model P-38 into their high-speed wind tunnel. They ran tests up to Mach 0.74. The results were both illuminating and terrifying. At high speeds, shock waves formed over the wing's upper surface. These weren't gentle pressure changes. They were supersonic discontinuities where air molecules literally piled into each other because they couldn't get out of the way fast enough. Behind each shock wave, the smooth airflow separated from the wing surface. Lift collapsed, drag skyrocketed. But here's the killer finding. The shock waves didn't affect the entire wing equally. They formed strongest near the wing's mid-chord point, roughly halfway between the leading and trailing edges. When lift collapsed at mid-chord, but remained higher toward the rear of the wing, the center of pressure, the point where all aerodynamic forces effectively acted, shifted dramatically rearward. That rearward shift created an enormous nose-down pitching moment. The aircraft wanted to dive more steeply, and simultaneously, those shock waves disrupted airflow over the tail and elevators. The pilot's controls, which worked by deflecting smooth airflow, suddenly had turbulent, separated flow to work with. They became useless. Kelly Johnson studied the wind tunnel data with growing understanding. The problem wasn't the tail, it wasn't flutter, it wasn't structural weakness. The P-38 was encountering a regime of flight that simply hadn't existed before. The Lightning was the first American fighter fast enough and clean enough to push into transonic speeds where the rules of subsonic aerodynamics broke down. They were pioneers in a deadly sense, flying into territory where theory couldn't help them. The solution, Johnson realized, wasn't to slow the aircraft down. You can't win air superiority by telling pilots not to dive. The solution was to change how the wing behaved at high speeds. Specifically, they needed to prevent that rearward shift of the center of pressure. If they could keep the center of pressure forward, the nose-down moment would be manageable. The elevators would remain effective. The pilot would stay in control. But how do you change the center of pressure on a wing that's already built? That's where a young Lockheed engineer named Ward Beeman came in. Beeman was working in Lockheed's aerodynamics department, and he'd been studying the NACA wind tunnel data obsessively. He noticed something interesting. The shock waves formed on the upper surface of the wing, but air was also flowing underneath the wing, on the lower surface. What if you disrupted that lower surface airflow? What if you put something in the way, a dam or obstruction that changed how air moved under the wing during high-speed flight? The idea seemed backwards. Conventional aerodynamics said you wanted smooth airflow everywhere. Adding obstructions created drag, and drag was the enemy of speed. But Beeman wasn't thinking about cruise performance. He was thinking about survival in dives. If you could disrupt the lower surface airflow in just the right way, you might be able to shift the center of pressure forward again, counteract the rearward shift caused by shock waves on top. Beman proposed installing flaps on the underside of the wing, not normal flaps that pilots used for takeoff and landing. These would be dive recovery flaps, small surfaces located outboard of the engine nacelles, positioned near the wing's quarter chord point. They would deploy quickly, extending downward 35 degrees in just 1.5 seconds. When deployed, they would create turbulence on the wing's lower surface, effectively reducing lift from that area and forcing the center of pressure to move forward. The nose-down moment would decrease. The pilot would regain authority. It was elegant, it was simple, and it might work, or it might tear the wings off when deployed at 400 miles per hour. There was only one way to find out. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. February 1943. A P-38G sat on the ramp at Burbank with a set of experimental dive flaps installed under its wings. Lockheed's chief test pilot, Milo Burcham, and his colleague, Tony LeVier, were scheduled to alternate test flights. The flaps were electrically actuated, controlled by a switch in the cockpit. Deploy them, and small hydraulic rams would drive the flap surfaces down to 35 degrees in less than 2 seconds. Retract them, and springs would pull them flush with the wing. On paper, the system looked robust. In practice, nobody knew if the wings could handle the sudden change in pressure distribution at high speed. Burcham took the modified P-38G up first. He climbed to 25,000 feet and established a high-speed dive. As the airspeed climbed past 350 miles per hour, he felt the familiar signs: tail buffeting, nose tucking under, controls getting heavy. He reached for the dive flap switch and flipped it. The flaps deployed with a thunk he could feel through the airframe. Immediately, the nose-down tendency stopped. The buffeting lessened. Burcham pulled back on the yoke, and to his amazement, the elevator responded. Normally, predictably, the Lightning pulled out of the dive smoothly, controllably, at a speed that would have sent an unmodified P-38 into an unrecoverable plunge. Burcham leveled off, retracted the dive flaps, and let out a breath he didn't know he'd been holding. He tried it again, dive to high speed, deploy flaps, regain control, pull out. It worked every time. The flaps didn't act as speed brakes in the traditional sense. They didn't dramatically slow the aircraft. What they did was more subtle and more important. They changed the pressure distribution over the wing in a way that prevented the center of pressure from shifting too far aft. The wing kept producing lift. The elevators remained effective. Physics, which had been the P-38's enemy, was now being manipulated to save lives. Tony LeVier flew the next series of tests, pushing the envelope even further. He deliberately entered compressibility lockups, let the aircraft accelerate past 400 miles per hour in near-vertical dives, and then deployed the flaps. Every time, control returned. The nose came up. The aircraft recovered. LeVier later reported that with dive flaps installed, he could push the P-38 to indicated airspeeds approaching 600 miles per hour, although post-flight analysis corrected for compressibility errors in the airspeed indicator. The actual speed was lower, but still far beyond what unmodified P-38 seconds could safely achieve. By late February 1943, Lockheed had proof. The dive flaps worked. They were reliable, repeatable, and could be retrofitted to existing P-38 seconds without major airframe modifications. Kelly Johnson wrote in his notes that they'd finally solved a problem that had haunted the Lightning program since Major Gilkey's near-death experience in May 1941. It had taken 2 years, 1 test pilot's life, and countless hours of wind tunnel testing and engineering work. But they had an answer. The Army Air Forces approved the dive flap modification in March 1943. The final 210 P-38J models, designated P-38J25LO, would have dive flaps installed on the production line starting in June 1944. That was the long-term solution. But thousands of P-38 seconds were already in combat theaters without dive flaps, and pilots were dying. Lockheed couldn't wait for production to catch up. The company designed retrofit kits, complete sets of dive flaps, actuators, wiring, and installation instructions that could be installed by squadron maintenance crews in forward areas. By late 1943, Lockheed had assembled several hundred kits. They were shipped to North Africa, Europe, and the Pacific. P-38 seconds already in combat would be upgraded in the field. Pilots who'd been flying with one hand tied behind their backs would finally be able to fight on equal terms. Then, disaster struck. In March 1944, a Douglas C-54 Skymaster transport, loaded with 200 dive flap retrofit kits, took off from the United States bound for England. The kits were urgently needed by P-38 units in the 8th Air Force, who were taking heavy losses over Germany. The C-54 approached the British coast at dusk. An RAF fighter on patrol spotted it. In the fading light, the pilot mistook the 4-engine Douglas transport for a German Focke-Wulf Turbluff 200 Condor bomber. He opened fire. The C-54, loaded with equipment and fuel, went down in flames. All crew members died. And 200 dive flap kits, enough to upgrade an entire fighter group, sank into the English Channel. The loss was devastating. Not just the crew, not just the equipment, but the timing. This happened during Tony LeVier's 4-month morale tour of P-38 bases in Europe. LeVier, Lockheed's test pilot, was flying a specially modified P-38J-25 named Snafu that had been upgraded to full production spec at Lockheed's modification centre near Belfast. His mission was to demonstrate to combat pilots what the dive flap-equipped Lightning could do, to show them that help was coming, that their aircraft would soon be competitive with the best German fighters. LeVier arrived at various fighter groups and gave technical briefings. The pilots listened politely. Most were skeptical. They'd heard promises before. They'd been told the P-38 would dominate. Instead, they'd watched German fighters dive away to safety, knowing that P-38 seconds couldn't follow. At one base, home of the 20th Fighter Group, LeVier sensed the skepticism turning to hostility. Words weren't going to convince these men. He needed to show them. LeVier climbed into Snafuperman and took off. He climbed to 25,000 feet while the pilots on the ground watched. Then he rolled inverted and dove straight down. Engines at full power. The Lightning accelerated like a dart, screaming toward the earth. Pilots on the ground rushed to watch what they assumed would be a crash. They'd seen this before. High-speed dives ended one way for Lightnings, in uncontrollable plunges or last-second bailouts. At 10,000 feet, travelling faster than any of them had ever seen a P-38 move, LeVier deployed the dive flaps and pulled back on the yoke. Snafuperman pulled out smoothly, precisely, with control authority that looked impossible. LeVier zoomed back up, rolled the aircraft on one engine for emphasis, and landed. When he climbed out, ground crew was silent. One pilot finally spoke. "Can you do that again?" LeVier did. 3 more times that afternoon, each time diving steeper, each time pulling out with casual precision. The message was clear. This is what your Lightning will do when you get dive flaps. You'll own the dive. No German fighter will escape you again. But the tragedy of the lost C-54 meant delays. Lockheed scrambled to manufacture replacement kits. Some P-38 units received them in late spring 1944. Others didn't get dive flaps until summer. And some squadrons flew the entire war without them, making do with careful airmanship and avoiding situations where they'd need to dive hard. The final half of all P-38 seconds built, roughly 5,000 aircraft, had dive flaps installed at the factory. The rest relied on retrofit kits that arrived late or never. For the pilots who got dive flaps, the difference was immediate and profound. Lieutenant Robin Olds, who would later become a legendary fighter, ace in Vietnam, flew P-38 seconds over Europe in 1944. He described engaging a German fighter at altitude, diving after him, and for the first time feeling the aircraft respond as he'd always wanted it to. The German dove hard, expecting the P-38 to stay high. Olds stayed with him, deployed dive flaps, and rode the Lightning down at speeds that would have killed him months earlier. He recovered at 5,000 feet, behind the German, and shot him down. Mission reports from mid-1944 onward tell similar stories. P-38 pilots who'd been fighting defensively, avoiding steep dives and accepting altitude disadvantages, suddenly became aggressive. German pilots who'd grown comfortable with the Lightning's limitations found themselves surprised. Intelligence reports captured after the war show Luftwaffe briefings from summer 1944, specifically noting that American P-38 seconds were performing differently. They could now pursue in dives. They were more dangerous. The tactical impact was measurable. Fighter groups equipped with dive-flap-modified P-38 seconds reported loss rates dropping by 30% compared to the previous 6 months. Kill ratios improved. Bomber escort missions saw fewer losses because P-38 escorts could engage and destroy German fighters rather than watching them dive away. The dive flaps didn't make the P-38 invincible. German Fu 190 seconds and late-model Bf 109 seconds were still formidable opponents. But the Lightning was finally competitive on terms that mattered. In the Pacific Theater, where combat often occurred at medium altitudes, the dive flaps had different implications. Japanese fighters like the Zero and Oscar were nimble but lightly built. They couldn't dive as fast as American fighters without risking structural failure. P-38 pilots learned to use boom and zoom tactics, dive from altitude, make a high-speed firing pass, and zoom back up using momentum. The dive flaps gave them confidence to push those dives harder and recover faster. Japanese pilots found themselves unable to escape. Major Richard Bong, America's top ace with 40 confirmed kills, flew P-38 seconds throughout his Pacific combat tour. By the time he reached his final victories in late 1944, he was flying a dive-flap-equipped P-38 liters. In interviews, Bong described the difference. The early P-38 seconds, he said, required careful energy management. You had to think 3 moves ahead, avoid getting too fast in dives, plan recovery altitudes. The dive-flap Lightnings were more forgiving. You could be aggressive, push hard, trust the aircraft to respond when you needed it. Major Thomas Maguire, America's second-highest-scoring ace with 38 kills, also flew P-38 seconds in the Pacific. Maguire was known for aggressive tactics, pushing his Lightning to its limits. He survived because his aircraft had dive flaps. The modifications installed starting in mid-1944 literally kept him alive long enough to become an ace. Tragically, Maguire died in January 1945, when his P-38 stalled during a low-altitude combat maneuver, not from compressibility, not from a failure of the dive flap system, but from the same physics that killed pilots in any fighter when they exceeded their aircraft's envelope at low altitude. The dive flaps validated something Kelly Johnson had understood from the beginning. The P-38's twin-boom design wasn't the problem. The engines weren't the problem. The airframe was fundamentally sound. What they'd been fighting was physics itself, and the only way to win that fight was to understand the physics deeply enough to manipulate it. Ward Beeman's dive flaps didn't eliminate compressibility. They didn't make shock waves disappear. They didn't let the P-38 fly faster than sound. What they did was give pilots control in a regime of flight where control had been impossible. By war's end, more than 10,000 P-38 seconds had been built. The final production models, the P-38 liters, incorporated all the lessons learned through years of combat. Dive flaps as standard equipment. Improved intercoolers that solved the high-altitude engine cooling problems the 8th Air Force had experienced. Boosted ailerons for better roll rate. The P-38 liters was, in many ways, the Lightning that Kelly Johnson had envisioned back in 1937. Fast, powerful, deadly, and finally, controllable in every corner of its flight envelope. The legacy of the dive flap modification extended beyond the P-38. The Republic P-47 Thunderbolt encountered similar compressibility problems, though less severe because of its different wing design. Republic engineers studied Lockheed's solution and developed their own dive flaps for the P-47, using the same principles. The lesson was clear. As aircraft approached transonic speeds, conventional control surfaces needed help. You had to manipulate the wing's pressure distribution to maintain authority. That principle became fundamental to jet. fighter design in the late 1940s and beyond. When Lockheed designed the P-80 Shooting Star, America's first operational jet, Kelly Johnson's team incorporated lessons learned from the P-38's compressibility battles. The P-80's wing was designed from the start to manage transonic flow. Dive brakes and speed brakes became standard equipment. Future supersonic fighters would use even more sophisticated systems, leading edges that drooped, trailing edges that split, entire wings that changed geometry in flight. All of it descended from Ward Behrman's elegant solution. Put something in the airflow to change the pressure distribution when you need it. The story of the P-38's dive flaps is ultimately a story about cost, not just dollars spent on research and development, though Lockheed invested millions. Not just the time lost, though 2 years passed between Major Gilkey's near-death experience and the deployment of a working solution. The real cost was measured in lives. Ralph veered and died testing servo tabs that didn't work. Countless pilots died in compressibility lockups before dive flaps reached combat units. And even after the solution existed, bureaucratic delays and tragic accidents like the C-54 shootdown meant some squadrons fought the entire war without them. The mathematics of war are brutal. In the European theatre, P-38 units made 130,000 sorties with a loss rate of roughly 1.1 aircraft per mission. That sounds low until you calculate the numbers. Hundreds of Lightnings lost, hundreds of pilots killed or captured. Some of those losses were inevitable, the price of air combat against a determined enemy, but how many could have been prevented if dive flaps had been standard equipment from the start? How many pilots entered unrecoverable dives because their aircraft lacked a modification that engineers knew would save their lives? The Pacific Theatre tells a different story, one where the P-38's strengths outweighed its compressibility problems. General George Kenney, commanding the 5th Air Force in the Southwest Pacific, couldn't get enough Lightnings. He requested them constantly, arguing that the P-38's range and twin-engine reliability made it perfect for operations over vast expanses of ocean. When P-38 seconds first entered combat in New Guinea in late 1942, they established air superiority almost immediately. Japanese pilots, accustomed to fighting nimble but short-ranged fighters, found themselves outmatched by Lightnings that could escort bombers hundreds of miles, fight for an hour over the target, and return with fuel to spare. December 27, 1942, marked the P-38's combat debut in the Pacific. 12 Lightnings from the 39th Fighter Squadron scrambled from Laloki Aerodrome near Port Moresby when radar detected a large Japanese formation approaching. Captain Thomas Lynch led the flight. Among his pilots was a young lieutenant named Richard Era, Bong, who'd nearly been court-martialed months earlier for unauthorized aerobatics in a P-38, including looping around the Golden Gate Bridge. Kenney had recognized talent beneath the recklessness and given Bong another chance. The 12 P-38 seconds climbed to intercept 25 Japanese fighters and dive bombers. When the engagement ended, American pilots claimed 15 enemy aircraft destroyed. Lynch and Bong each claimed 2 kills. The compressibility problem that plagued European operations mattered less in the Pacific. Most combat occurred at medium altitudes, where P-38 seconds could dive aggressively without hitting their critical Mach number. Japanese fighters like the Zero and Oscar were magnificently maneuverable but lightly built. They couldn't dive as fast as American fighters without risking structural failure. P-38 pilots learned to use vertical tactics, boom and zoom, diving from altitude to make firing passes and then climbing away before Japanese fighters could respond. Richard Bong became America's top ace, credited with 40 confirmed kills, all in P-38 seconds. Major Thomas Maguire, the second highest-scoring American ace, achieved 38 victories, also exclusively in Lightnings. Both men flew dive flap-equipped P-38Js and P-38Ls by the time they reached their final tallies. The dive flaps gave them confidence to press attacks harder, dive steeper, and recover faster. In interviews, Bong described the P-38 as forgiving aircraft that brought him home when other fighters would have killed him. The twin engines provided redundancy. On multiple occasions, Bong nursed damaged Lightnings back to base on one engine. The concentrated nose armament, 4 50 caliber machine guns and one 20mm cannon, delivered devastating firepower without the convergence problems of wing-mounted guns. Up next, you've got 2 more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them. Out! And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.